All right, welcome to Data Science Club number 17. We're going to do essentially the same tutorial we did last week in R, but this week we're going to use Python. And since we have already created our Python environment in some of the earlier videos, we're just going to use that. So we shouldn't have to install anything, and we should be able to just get through the whole tutorial today. So we'll see how it goes. If it's going long, we'll break it up into two. So we are going to be using this machinelearningmastery.com machine learning in Python step by step. It's in the comments of the videos, or the description for the video if you scroll down a little bit. And yeah, so that's what we're going to use. And then to run the code, we're going to use the UAB Research Computing Compute Cluster Chiha. You go to rc.uab.edu, and if you are a UAB student or faculty or staff, then you can get access to this and run things on the supercomputer directly just because you have a Blazor ID. If you don't have this, you can still install the same environment we have. If you go to the first video, it's just a matter of troubleshooting your Anaconda environment. Feel free to shoot us a message if that doesn't work out. The other thing before we get started is this is the beginning of the semester, and so welcome to everybody that is seeing this for the first time doing the Data Science Journal Club as a course. I sent out an email today with the requirements for the course, so feel free to ask questions and drop by anytime to bug Ravi and me about any of this stuff. So yeah, with that, do you have anything else to add on that, Ravi?
No, that's basically it. Just welcome to the students who are taking this course, and like William mentioned, we'll be here in the office hours that William mentioned in the email on Mondays in Civitan, 10 to noon, and Wednesday 1 to 3, and Thursday again 10 to noon in Edge of Chaos.
Yep. And if you have any questions, just email us or comment in the YouTube video, and we'll get back to you as soon as we can. All right, so first thing, we know we're going to need a Jupyter Notebook for this. So we're going to open up Interactive Apps, and we're going to click on Jupyter Notebook. And then we're going to put our Jupyter Notebook in our data user directory. That's fine.
Yeah, so this dash notebook there basically means that's where your Jupyter Notebook is going to start. So one of the things with Jupyter Notebook is you have to specify the place where it starts. If you don't specify, it starts in your home directory by default. Generally on the Chiha cluster, we keep most of our scripts and all of our data on the GPFS location. That's the data location. So specifying that over here will start your Jupyter Notebook there, and then you can go down the tree in that location.
Yep. So let's see, we're going to specify 2 hours, but this should take just 30 minutes or so. And so we will launch. And seed session was successfully created. And we'll just refresh this page a couple of times. So right now what's happening is on the back end, the supercomputer is scheduling our compute session. So we asked for a GPU node. All right, and then now it's starting up. You see those blue. And now we're running. All right, so we should be able to click this Connect to Jupyter, and it shows up. If you've run some of the previous tutorials, you have this rc-dsc folder. That's what I'm going to start up in so that we have a common folder to work with. And then I'm going to create a new, and I'm going to use the NBOTW. That should be the same environment that you create in that Anaconda environment video that we have for our first video on the channel. So just check that one out, and then you'll have the same environment. So by doing that, now I have a Jupyter notebook, and we can start playing around with this. So let's go over to this tutorial and see what's going on over here. So in this tutorial, he talks about downloading and installing. We're going to skip over that because if you've done the previous videos, you have already done that. And we're just going to work on the loading the data sets and creating the machine learning models. So let's scroll down and find where that starts. All right. Going. All right, so again, we don't need to download and install because we've already done that.
Yeah, all of the libraries that are mentioned over here should be in your notebook of the week environment where you started your notebook.
Yep. And if it's not, you can always check out these links here that should be helpful, or you can come into office hours and we'll be happy to help you get that set up. He's doing these tutorials just in a Python script, not in a Jupyter notebook. So one nice thing is because we're in a Jupyter notebook, when we start printing stuff out, it'll show up directly inside the notebook. So I just copied, and now I'm pasting that code, and then I'm going to run it. And so then you can see as it loads the libraries, it's telling us what versions we have of everything. And indeed, we do have all of these libraries installed already, so that's great. We should be good to go. All right. I don't think we're super far off from the versions he's got. Actually, we're a little bit lower on the Python, but that's okay. Shouldn't matter. We should be able to do pretty much everything.
Yeah.
All right. So now we're going to load the data. So first things first, we got to import some more libraries. All right, so let's do this. And we already imported pandas earlier, so we don't have to re-import pandas. So I'm going to comment that out. Then I'm going to run this. So pandas is the data manipulation toolbox that we like to use in Python. And so this is importing some plotting tools with that, and with this matplotlib, and then we're importing a lot of different model classification and model selection metrics kind of things from scikit-learn.
Yeah, I had a look at his tutorial a little earlier, and so the reason for getting the matplotlib library is that we are going to be visualizing data, and the plot function is going to help us in doing that.
Okay.
Apart from that, most of the other libraries there's that scatter matrix from pandas, like William already mentioned. That's a data manipulation library, and that's one of the essential libraries in data science. And after that, it's mostly scikit-learn methods that are being imported from the scikit-learn library.
Yeah, so I'm not sure why this was included in the loading the data part, aside from that just is importing the plotting functions that you'll need. But that's okay. We'll need all this stuff anyway later, so it doesn't hurt to go ahead and load it there. And then now we're going to actually load the data set. So this is where pandas comes in handy. So you see how it says we have the URL, which is the website address of the database that we're going to load. And then the names of the columns associated with that CSV file. And then this pandas.read CSV doesn't care that this CSV file is not on our computer. it should import it directly from the website there. So let's see how that works. So we're going to paste this and we're going to run. Okay, so that worked. Again, if you've seen previous ones, you should be able to go dataset.head, and it'll give you the first 5 rows of that data set, and so you can get a feeling for what's going on in there. So let's scroll down. It looks like we're going to do a little bit of data set exploration stuff, so that should be good. So data set shape, this is nice because this tells us what size our data set is. So we already see that we have 5 columns, but if we run this, it will also tell us that we have 150 rows. So we have 150 observations or samples in this data set with 5 features per sample. All right, and we already ran the dataset head command, and you can see if you specify a number in there, it will give you more rows to look at. So we're going to skip that because we've already done that. But if you do this dataset describe, it's very similar to head, except instead of giving us instances of each row, what it does is all right, I'm going to paste that. It actually gives us summary statistics for each column. So it tells us how many are there, what the averages are, standard deviation, and then the quartiles and the max and min. So really helpful if you don't have a handle on what your data is doing already. This kind of gives you a feeling for what's going on with it.
Yeah, and I mean, in some of the ways that it's useful is like in this particular data set, there is nothing that's missing. Otherwise, you'll see there would be a difference in count between different columns.
Mm-hmm.
That generally just means that some of the rows don't have that particular value. That's where the data manipulation part starts coming in, where you have to curate your data so that it's ready for data science.
Mm-hmm.
I mean, there are a bunch of things you can do if something is missing. Like either you can remove the entire row. That's a very hard-handed method.
Yeah.
There are others, like you can take an average out of the of all the values in the row and put those values over there. And so it particularly depends upon your data. If you have, like today we were talking to someone who had 5 million rows over there, it might not matter if you remove a couple of rows.
Yeah. If you had a few missing values in your 5 million row data set, that's probably fine.
Yeah.
All right. So now what we're going to do is look at class distribution. So when you're running machine learning things and you're trying to classify a data set, if you have an uneven number of each group, like let's say we do this, and let's see how much is in there. Okay, so there's 50 of each class. If we had 100 of this iris setosa and then 10 of each of these other ones, then over 90% of our data set would be one class. And so most machine learning models will then just learn to always say that it's in this one class, because that way it can get 90% accuracy. And so it's really nice to take a look at how many of each item you have in each class, so you make sure your data set is roughly even, so that you're learning features that genuinely differentiate the classes and not just on average is 90% of the time it should be this one.
Yeah, that's a good point. And like William mentioned, that they need to be roughly similar. Like this data set is perfect. It's 50-50-50, which might not be the case for the real data that you have. But it would be a good idea if they are pretty close and roughly in the same range.
Yeah. All right. So now we're going to do data visualization. So this is nice because we can start getting plots of what these features look like and give us more of a feel of our data before we start doing machine learning things. The better you understand your data before you run a machine learning or data science technique, the better your model will be in the end, just as a general rule of thumb. So let's paste this over here and run that and see what shows up. All right, so this shows us, we do have a fairly wide distribution in each one of these features. Doesn't really tell us a whole lot at this point. It's not lopsided, which is good.
Yeah.
And let's see, we can get histograms. We can just look at these ones. I'm not sure. Without having this per class, I'm not sure what this tells us quite yet. If one of these was really lopsided, that would give us some indication that something weird is going on. A nice thing here, you see that there's a distribution here and then a second distribution over here. So perhaps we can maybe guess that one of our flowers lives over here and the other one has this petal length, and so that parameter will help us differentiate things. Perhaps. We'll see. All right, multivariate plots. So this is where we get into, I think this is by class. Oh no, this isn't by class. This is looking at the covariance of these factors. So let's plot that. That's pretty interesting. All right, so let's paste that in there. And run. All right, so this is nice because this tells us, for instance, that sepal length and petal length look like they're pretty strongly covarying. So if we had to do a feature reduction, we might take out one of those two, for instance. All right, let's keep on rolling. All right, so now we're actually going to start running some algorithms on this data. And this is great because everything that we've done so far, you could essentially just, and everything that we're going to do still yet, you could take out this data set, plug any other CSV file that you have in there, and get these similar types of results, but on your data. So this is really portable, which is really nice. So first thing we're going to do is make a training and testing split of our data. All right. And so the reason for that is if we're creating, if we're creating a model that we want to be generalizable, so it's going to work on multiple different types of data sets that cover the same types of features, then we want some way of knowing that our model doesn't just work on our data that we have, but it might work on other data sets as well. So by taking our data set that we have in the first, those 150 values, and then splitting it into a training and a testing data set, allows us to get a feel for that. Because if we have really good training accuracy, but then our accuracy on the validation data set is low, then that lets us know that we're overfitting. So this is really important when you're thinking about the repeatability of your model, the reproducibility of your results, is doing this splitting into training and testing.
Yeah, and if you notice in the arrays that we have defined, we have the X that's going to be all the features.
Yep.
That we have, like sepal length, width, and petal length and width. And then the Y variable is just the type of flower.
Yep.
And that's, so once you have defined those, then you are just doing the split using that train test split.
Yep.
Okay.
And this is a function inside of scikit-learn to just make it simple to do this train test split. You could do it manually if you like, but this is a nice way to do it. You just have to specify how big of a percentage you want to go to your testing and validation data set. And so right here we specified 20%, and that goes in here in this test size. And then in this X and Y validation, there will be 20% of the data, and then the rest 80% should be in the X and Y train.
Yeah, and generally that number is like depends upon how large your data set is. But if it is like this much length, like 150 values that you have, then 20% is a decent number.
Yeah. So yet another thing that you can do to help improve your model robustness is something called cross-validation. And so that's what we're doing next. This thing here is just setting it up. Seed is just the random seed that's going to go into this. And then how we score the models is going to be based on accuracy. So let me run that, and we'll go to the next part. Yeah, as specified here, the random seed doesn't matter. This is just for if you're trying to make sure you get the same results every time, you might want to specify that. And these are just the parameters that are going to go into the cross-validation. What cross-validation does is it takes our training data set and then splits it up into another 10 training and testing data sets, so that then we can build our model with those subsamples in mind, so that if there are any outliers in our data set, they have less of an influence. So let's see, let's go down, and now we're gonna start generating our algorithms. So let's take a look at what this does here. Paste that in here, and then we're gonna run. All right. I think we already...
It already ran. It was only 150.
It already ran. It's that fast. All right. So what's happening here is, so we're creating a list called models, and right now it's empty. And then what we're going to do here is we're going to append or add to the end of the list each one of the models. And then when we get to this for loop, what this is doing is saying for each model in models, so each model is associated with a name that's in the quotes, and then the models over here, defined right here. So for each of these models, we're going to run a k-fold cross-validation, and then we're going to get our score on the training set with this other function here. So model selection.kfold says, okay, create my 10 cross-validation data sets. And then model selection.crossval score says, okay, using this model, the X-train and Y-train data sets, do a cross-validation with these 10 folds that are specified in k-fold, and use accuracy, which we specified earlier up here, for the metric, and then give me the score. And then append to this results list that we started, and append the names to this names list that we started up here. And then it's going to print out the results. So what we found here is it looks like logistic regression did 96% accuracy, linear discriminant did 97%, k-nearest neighbor looks like it did 98%. Let's see how close we were to his results. Okay, it looks like we were about the same. Because there's some randomness in how these algorithms are initialized, you may not get exactly the same results but the results should be comparable.
Yeah, yeah, and I mean there are a lot of places where you can introduce variation. Like you could have had 30% saved as 30% of the data saved for validation,
Mhm.
which might have introduced some sort of variability. We are using cross-fold method, so it might not have impacted it too much, but a bit for sure.
Yeah, and if we had changed our random seed up here, we most likely would have gotten a different result. So actually, we can try that real fast since it runs so quickly. So if we change our seed to 42, and we run that, and we rerun our model, it looks like our
Okay, and it's still doing good, but cart has improved.
yeah, the decision tree seems like it's doing a lot better, and support vector machines is now doing
We
99%. Let's try something different. Yeah, and then it looks like support vector machine is still doing the best out of all of them, and KNN is still doing pretty good.
Yeah, decision trees has gone down a little.
Yeah.
How was the vector machine doing with 7?
I don't know. I didn't pay attention. Let's rerun that. Okay, so it was doing pretty good, 99%. All right. So now we're going to come down and we're going to plot the accuracy of these algorithms.
I mean, it's very obvious that the vector machine is doing the best, but it's still good to plot them.
It's still good to plot it. Yeah. They're all doing pretty good though. The width on these box plots, I believe, is the distribution of the accuracies in each one of the 10 folds of the cross-validation.
Mm-hmm.
So that's why this is a box plot and not just a single value. All right, so now we want to make predictions, and this is why we split up our data into the testing and training data sets, because now if we run our test and we get worse than what we got with our training, then that means that model maybe wasn't the best overall. So let's copy and paste this and see how well our k-nearest neighbor does, since that's one of the ones with the higher accuracies, 98%. So if we pop that into here, all right, and then we run. All right, so now what this shows us is our confusion matrix. And so we can see out of the, let's see, 27, 30, out of the 30 data points that we reserved for testing, we misclassified 3. So we got 90% accuracy. So we got 90% training or testing accuracy when we got 98% training accuracy. So we're probably a little bit overfit to our training data set. So it'd be nice to have more data and maybe specify some parameters so we're not building as complex of a model on the front end to try to reduce that overfitting.
Yeah, and that is something that you might see a lot in your data as well. I mean, suppose those 150 rows were just an aberration, and the actual, if you took a sample out of 10,000 of these, then the result might have been completely different. But you just trained on those 150, so your results are going to be a lot worse on the actual validation data set.
Yeah, so we can do the same thing with the support vector machine, since that said it was 90% accuracy. Let's just pop this in here. Technically, for completeness sake, we should change these other variable names just because of good programming behavior, but we don't have to. Those are just names, so we can rerun it and see. So we got 93% accuracy. So the support vector machine is actually doing a
Better.
better job of being generalizable, but really it only correctly classified one more sample than the KNN did, which the KNN stands for K nearest neighbor. So you can see how easy it is to switch out these models and really test for which one is going to be the best in your situation. And I really like this guy's blog because he kind of hits the nail on the head. Like, you don't have to know everything in order to get started. And you can see that this tutorial didn't take us very long, and you could, grab an Excel spreadsheet on your computer and start running machine learning today on that, and start to get real results. So again, just feel free to play around and come into our office hours and ask us questions. We're not experts, but we're just trying to figure it out just like you. So yeah, stay tuned, like the video, subscribe if you haven't already done that. And if you're in the course, we look forward to getting to know you guys better. And yeah, just ask questions. That's what we're all doing. So yeah, anything you got to add, Ravi?
That's it.
All right.
Thank you.
Yeah.